Hello dear students, welcome to Pen and Paper Chemistry on YouTube. Are you ready with your pen and notebook to continue the learning on phenols? We have already dealt with the properties involving the breaking of the OH bond, and will now be moving on to properties wherein phenol shows electrophilic aromatic substitution reactions. So as you can see, there are so many of them. What does this tell us about the behavior of phenol? Yes, that it is a very reactive compound when it comes to electrophilic aromatic substitution reactions. What explains this behavior of phenol? Yes, of course, the presence of the OH group on the benzene ring. But what does that OH group do? We have already discussed this in the previous videos. So, go ahead and draw the resonant structures or the canonical structures of phenol. Let me see how many of you are able to get that right. Once you've done for phenol, also if it loses a proton, remember we talked about the phenoxide ion? Just for quick recall, can you draw the resonating structures of phenoxide ion? Draw it. I have left these blanks for you to fill. Please fill in these blanks for me. As you are completing your notes with me, please fill in the blanks. That means draw the resonating structures of phenol. Now, once you've drawn the resonating structures, you will see that in the case of phenol, firstly, the ring gets activated. Why does it get activated? There is a high concentration of electrons on the benzene ring. Now, because the OH group has released the electrons towards the benzene ring, what will happen? If there are high electrons, that means there will be something which is electrophilic, something which is electron loving will be attracted towards the benzene ring, right? So if it is attracted towards the benzene ring, that means my OH group is ring activating. It is activating it towards further electrophilic substitution reactions, right? Further electrophilic substitution. This can only be explained if you draw the resonance structures of phenol. Unless you do that, you will not be able to understand this concept clearly. So if you do not know, please go back to the set of videos in phenols where we have discussed this in greater detail. Now let's see, where will this electrophile like to go? Yes, of course, at positions where there is negative charge, because it is electrophile, electron loving. Phile means loving, right? Phile. So it likes to go at the negative centers. So what are those negative centers? With respect to the OH group, these are the ortho and the para positions. So if you have the benzene ring and there is a substituent already present, the first position next to it is the ortho, second position next to it meta, third position or directly opposite to it is para. So what will this position be called? What will this position be called? Yes, go the other way around. Now if you see, first position with respect to this is ortho. The second position with respect to this is meta. So there are two ortho positions, two meta positions and 1 para position. So with the result, now there are electrons at ortho and para positions. So we notice that in the case of the presence of OH group in the benzene ring, there are so many reactions wherein the substitution is taking place at the ortho and the para positions, but there are reactions where substitution is taking place at all the 3 positions, that is all the 3 ortho and the para positions. OH group is so highly activating because it is releasing electrons towards the benzene ring, right? So again, what you can do is you can draw this flow chart, take a screenshot, take a printout, or best, draw it yourself. Once you draw it yourself, you will realize that it is so relatable. It's so easy to use when we are going to write the reactions further on. That's what I'm going to do. I'm going to put my flow chart on the on the left hand side top, as you can see, and use it as a guide to tell me what reactions I have to teach today. So let's get started with the first one. Nitration. What is nitration? A replacement of the hydrogen of the benzene ring by the nitro group, by the NO2 group. Now what I have done is, just like I've done it in the flow chart, I have put 3 arrows. 3 arrows, but teacher, in the flow chart, you've done only 2 arrows, right? Then how come 3? Oh, I'm going to combine what we are going to do further in the flow chart and explain to you what is the meaning of the third one that I have put over here. Okay, so would you like to complete the first reaction for me? That is phenol with dilute HNO3 at a low temperature of around 25 degrees Celsius. Go ahead, draw. We will have ortho and para nitrophenol. So ortho nitrophenol and para nitrophenol. Now you see, in this case, why are we getting a mono substituted product? Only 1 hydrogen has been substituted. This can be explained with the help of the reagent that we've taken. It's a dilute HNO3. Dilute HNO3 means lower concentration of nitric acid. Lower concentration of nitric acid means lower concentration of NO2 positive in the reaction mixture, right? Can you name these products, please? Ortho nitrophenol and para nitrophenol. Now I will put a statement over here, and I would want you to try and explain that they can be separated by steam distillation. They can be separated by steam distillation. How can I separate both of them? Both are similar compounds. On what principle can I separate them by steam distillation? Think about it. Think about your learning so far and connect the dots. Could you think of an answer? Okay, then if you did, why don't you write the keyword in this answer, and then let's see whether it matches with what I'm going to give you here. Do these structures remind you of some concept? Look at it. It's nothing. Orthonitrophenol I've written in an expanded form. Paranitrophenol again written in an expanded manner. Look at the structure here. It's forming a 6-membered ring by what bond here? Hydrogen bond. Whereas this kind of formation, oh, look at that. It's so far. Can I form a hydrogen bond? Oh, no way. are we going to form a stable ring? Okay, let's drop the idea of forming a hydrogen bond here, right? But what can happen is it can form a hydrogen bond with another, let's say, a water molecule over here. Yes? Oh, yes, this is possible. What's the difference here? Yes, this is intramolecular hydrogen bond. Now, just like it formed a hydrogen bond with water, supposing there was another molecule of paranitrophenol, do you think it would be able to form a bond with that? Oh yes, why not? We can form friendship here, right? But what type of hydrogen bonding would this be? Yes, this is intermolecular, between two molecules. Intermolecular hydrogen bonding. Now, because it is forming intermolecular hydrogen bonding, we will need a higher amount of energy in order to vaporize it. These molecules are closer to each other. Whereas here, this is limited to itself. So, with the result, orthonitrophenol will have a lower boiling point, whereas paranitrophenol will have a higher boiling point when I compare ortho and paranitrophenol. Can you please find out what is the boiling point of each one of them? So which one of them will vaporize first? Yes, absolutely right. Orthonitrophenol will vaporize first. That is why we say that they can be separated by steam distillation. So tell me, did you get this right? Did you get the word hydrogen bonding? Intramolecular and intermolecular. Look at the spelling. I-N-T-R-A within. Inter. I-N-T-E-R. These concepts have been dealt in a greater detail under the videos on hydrogen bonding. I have completely covered hydrogen bonding separately on the channel. So if you want to refresh your knowledge, you can go to that playlist. Let us now come to the next reaction where phenol is being treated with concentrated HNO3 and concentrated H2SO4. Now, we should not forget over here that concentrated HNO3 is a very good oxidizing agent. Anyway, let's carry out the reaction first. So, what we will form over here is, it's because concentrated, that means there's a high concentration of NO2 positive ions. With the result, I get a trisubstituted product. So NO2, NO2 and NO2. Would you like to try and name this product? So obviously our position number 1 is OH, 2, 3, 4, 5 and 6. So it becomes 2, 4, 6 trinitrophenol. In the common system, it is also, or commonly it is also known as picric acid. This picric acid are actually yellow colored crystals. So probably you may want to write it with a yellow color so that it's easier to remember. Okay, so that's what I'm going to do here. I'll write it as picric acid in yellow. Now, these picric acid crystals which are to be formed according to this reaction, actually when we carry out this reaction, the amount of picric acid that we get over here is very poor, in the sense we get a very poor yield of picric acid. Why? I gave you the reason before we started the reaction. Concentrated HNO3 is a very good oxidizing agent. So, concentrated HNO3 oxidizes the phenol. And because it oxidizes the phenol, not much is available to react with the NO2 positive ions which are there in the solution. By the way, in a separate video, we have also dealt with the mechanisms of electrophilic aromatic substitution reactions. So in case you want to familiarize yourself with mechanism, there's a separate set of video. Now that we've got a poor yield of picric acid, it will explain why I have written the third step in this reaction. So what I'm going to do is, I'm going to first treat the phenol with concentrated sulfuric acid. So what do we get over here? Our first product, because of course we will get the sulfonated product, so OH. We will get SO3H substitution by the sulfonic acid group when treating with concentrated H2SO4. But because the ring has gotten activated already, what we find is if we take a high concentration of the concentrated H2SO4 and continue the reaction longer, we get 2,4-phenol disulfonic acid. Sorry, it's phenol 2,4-disulfonic acid. What mistake did I make? Yes, I said 2,4-phenol. It's not 2,4-phenol, it's phenol 2,4-disulfonic acid. And then I am going to carry out its nitration. Again, with the presence of concentrated HNO3. So we've broken down this reaction into two parts. Now SO3H group, which is present over here, is a very good leaving group. It is happy to be on its own because it can undergo resonance. So we form our desired product, that is, go ahead, draw the structure, picric acid. What is picric acid? 2,4,6-trinitrophenol. Now we are not going into the details of this mechanism because it is not required for your grade 11 and 12. A detailed mechanism may be required for your entrance examinations, but for the student group that I am targeting in these videos, I think I will limit myself to this. There is no end to knowledge, to be honest, no end to it. The more you have, the more you want. Have you written down the reaction? So this method, the third arrow that we've drawn, this is the commercial method of preparing picric acid, what we call as the industrial method of preparing picric acid. Why would we want to prepare picric acid on an industrial scale? Think about it. Now look at your chart and try to complete the reaction on sulfonation. That's the next reaction we are going to talk about. And you have the chart in front of you, right? You notice the conditions of the reaction. Reacting phenol with dilute sulfuric acid at low temperature of around 15 degrees Celsius and concentrated H2SO4 at around 100 degrees Celsius. Now there is a logic behind each of the reactions, but our limitation is that we need to stick to our syllabi. And what do we form over here? Phenol, and the sulfonic acid group will be at the at the ortho position. So how will you name this product? 2-phenol sulfonic acid, right? Okay. And how will you give the IUPAC name of these compounds? When you see according to the IUPAC nomenclature, our sulfonic acid group is the principal functional group. And then in that case, OH becomes the secondary or the follower. So you'll have 1, 2, right? And whereas here it will be 1, 2, 3 and 4. So now when your OH is the secondary functional group, how are we going to name it as? Go ahead, write the name 2-hydroxy benzene sulfonic acid. Easy to understand? Yes? Okay. Now go ahead and write the name of the second product yourself. Good going so far. We shall continue with the reactions of halogenation in the next video as well as Friedel-Crafts. So stay connected when we continue with our learning. Take care. Have a water break.